In this video, I will explore the flux integral in order to better understand what this really means. So this is the simplest form of a flux integral. However, it may not be the best for understanding intuitively what this is saying. So we start off with our surface S that is two-sided. It's oriented, so it's two-sided and has a tangent plane at every point. And it has a normal vector, and because it is two-sided and has a tangent plane at every point, then it has a normal vector given by this equation. It is also written in its parametric form as x equals x, y equals y, and z equals g, which is a function of x and y. Okay, which is the most general form, most general parametric form that a surface can have. Okay, so we go to this equation. All right, now we have to recall that the vector, any vector, can be written as a product of its magnitude and its direction. So the magnitude of ds I will write without the under tilde. Okay. So then when you substitute this into this equation, you get this using some properties of dot products. Okay. Now we have to remember what ds is. ds is equal to the square root, if the surface is parameterized this way, dg dx squared plus dg dy squared plus 1 dA. Okay? So now if we substitute this equation for the normal vector and this equation for the magnitude of ds into here, then we get this. Okay. Now as you can see, using more properties of dot products, these cancel out. Okay. And then if we let the components of f equal to p, the x component equal to p, the y component equal to q, and the z component equal to r, then we get this equation. But what I'd like to highlight is this form of the flux integral, because I think that it provides the most insight into what this really means. So recall that the component of A in the direction of B is equal to the dot product of A and B divided by the magnitude of B, which doesn't have an under tilde because it's a magnitude. Okay. But what about the special case when B is in fact a unit vector? So if B is a unit vector, then you're dividing by the magnitude of B, which is 1, which is just a dot product. So that means that the component of A in the direction of B would be just a dot product between A and B. Okay? So conveniently, this is the case here. So the flux integral is really the dot product of the vector field and the normal vector over, and you add all of those up over the surface. Okay? So now that we know it's just the component, the flux integral is just the component of the vector field in the direction of the normal vector over the whole surface, then that gives us some more insight. Which means if our vector field is, say, a velocity field of a fluid, then the flux integral is the rate of flow through S.